Hi, my name is Dmitry Vyukov, and my talk is about syzkaller coverage-guided kernel fuzzer. So first I'm going to talk about background, about problem space, then about implementation details, then about results that we get, and at the end a bit about future work. So I work at Google in dynamic tools team, and we do a set of tools. We also do some bug provocation tools, in particular libfuzzer, gofuzz, and syzkaller, and also some fuzzing automation and coverage tools. So some of them are older, and you hopefully know about them. Some of them are pretty new. For example, guipa-san and kc-san are our latest hotness, so maybe you want to check them out later. So we did our tools for user space initially, and around 2014 we started looking at the kernel. And by kernel I mean Linux kernel. We started looking at the kernel as a place where we can bring our expertise and also create tools. So first of all, we created a prototype of address sanitizer, which finds use of the free and out of bounds. So this is the first tool you want to have in your toolbox. But then we hit a problem. So those are dynamic tools, which means they are only as good as your tests are. They only detect bugs that actually happen on some load. So if you don't have any good load, then they will not find any bugs. And we couldn't find test suites for kernel, or we couldn't build them, or we couldn't run them. We booted kernel, we ran some user space programs, we found few bugs with address sanitizer, but it feels that it's not enough. We're not getting enough benefit of the tool. And around the same time, we started looking at fuzzing and user space as a technique to actually get some load and provoke more bugs and detect more bugs. So in essence, fuzzing is a very simple thing. You generate a random input, you feed it into a program, and you see what happens. Like, did it crash or not? But if you feed completely random data, most likely you will not find lots of bugs, because most likely execution will bail out on the first if condition in the code, and you will not actually cover a majority of the code, right? If you feed completely white noise. So the current state of the art in fuzzing is considered to be code coverage guided fuzzing. And in particular, tools like AFL, honfuzz, gofuzz, libfuzzer are all coverage guided fuzzers. So what is coverage guided fuzzing? You start by building your program with code coverage instrumentation, and then you collect corpus of inputs. You may take them from unit tests or somewhere else. This step is actually optional. You can start, let's say, with just one input. Then you choose one random input from the corpus, and you slightly mutate this input. For example, you flip some bits, or you insert or remove bytes. Then you execute this program and collect code coverage. And then you see if this program gives new coverage, so it covers some code that you never covered before with any of the previous programs. Then you add this program back to the corpus. And this last part repeats in an infinite loop, essentially. So let's see how it works in practice. Let's say we have this piece of code which parses an input, and to get to the last line that potentially may contain a bug, we need to provide an input A, B, C, D. So ABCD is 4 bytes, and if we try to guess it completely blindly, we will need about 2 to the power of 32 iterations to guess this. Right? So even for this simple and small piece of code, we'll need 4 billion attempts, which doesn't sound too good. So what happens with coverage-guided fuzzing? Let's say we started generating some random inputs, and in approximately 256 iterations, we generate input that starts with the byte A. At this point, when we execute, we'll get to the second line of the code, and we will say, oh, we actually never get to the second line of the code. This is new coverage, so we add input A back to the corpus. Then we'll continue this process, and approximately in 256 iterations, we will get input A, B. And at this point, we'll get to the third line of the code. Again, it's new coverage, so we add it to the corpus. And so on, and we will guess the ABC and then ABCD. So in total, it will take approximately 2 to the power of 10 or 1,000 iterations now to guess this input. So you may compare this to 4 billion iterations. coverage-gated fuzzing more or less turns exponential problem into polynomial because of this incremental progress and constantly persistent the progress in the corpus. So it's a bit reminds of dynamic programming. And there's a famous example for IFL how it generates valid JPEG image out of nothing. So the advantages of this approach is that it's efficient. It also gives reproducers because those inputs are by definition immediately reproducers if they trigger a crash. And it's also great for regression testing because the corpus by construction, it's a set of programs that gives us the maximum coverage. Okay, so existing kernel fuzzers, they were a bit simpler. What they did essentially, they executed an infinite sequence of random system calls with random arguments. So they had some knowledge of argument types. For example, if syscall accepts a file descriptor, they will try to pass some file descriptor in that position and so on. But still, it's just that. It's just an infinite sequence of system calls. And the problems with this approach is that it tends to find much more shallow bugs, and it frequently doesn't provide reproducers. So you can restart it with the same seed, but if you run it for an hour, the chances that you will trigger the same bug again are close to zero. It also doesn't help with regression testing every time you start from scratch. And the existing tools also had some issues with automations because for kernel it's not as simple as a small bash script. Okay, the question is how can we apply this nice idea of coverage-guided fuzzing to the kernel? And it turned out to be not that simple. There are several problems. First of all, what is an input? User space fuzzers usually consider input as just an array of bytes, so some blob, and which doesn't have any structure. So how do you turn this blob into some load on the kernel? And then how do you mutate this load on the kernel? Then user space fuzzers usually assume that all inputs are completely isolated, deterministic, and reproducible. So if you run the same program second time, you get exactly the same coverage and the same result, and this is totally not true for kernel. Also, for kernel, we have enormous input space. So one system call can have input space that is similar to that of a typical user space fuzzer. And we have thousands of system calls, and we also need to choose some set of them and execute in a particular order. So I think input space is at least 3 orders of magnitude larger, maybe even 5 or 6. Then there are some issues with coverage. User space fuzzers, again, assume that coverage is completely deterministic, stable, and a function of the input. But it's not true for kernel, because there are other processes, there are background threads, there are interrupts. Sometimes kernel even contains some intentional non-determinism. And we get flakes from malloc and scheduler. For example, malloc on low memory can start to do swapping and call into file system, and we see all of this as this kind of coverage for our input. Then there are issues, other set of issues. For example, if we create a pipe and try to read from it, it will block because the pipe is empty. So we don't want to stall forever on this read now. Also, provoking races is important. User space fuzzers usually assume that multi-threading just doesn't exist, that all programs are single-threaded, races don't cause bugs, and so on. But for kernel, it's very important to also provoke races. And then there's a set of operational issues. For example, user space fuzzer typically, after triggering a crash, it will save the input to disk. But if the kernel underneath you just collapsed, you can't do anything anymore. Maybe the image is destroyed as well. And for example, if you try to fuzz and you call reboot system call, then it will appear as you kind of crash the machine, but it's actually very intentional. And reboot system call is very obvious instance of this, but there are lots of kind of more complex scenarios that has the same outcome. When you crash the kernel, that's actually intentional, or you DOS kernel. Okay, so kernel fuzzing is different, and two key takeaways. One is that you need to be smart. Being smart becomes really important. because both the input space is at least 3 orders of magnitude larger, and your execution speed is at least 3 orders of magnitude slower, because you need to create processes, you do system calls, you block on blocking system calls, and so on. So it's 6 orders of magnitude at least. And to give you kind of, so that you understand how bad it is, in user space you can get something like 100,000 inputs per second tested. So it's pretty good. You can afford to, say, execute 1,000 of inputs that are completely nonsense and doesn't help you in any way, and it's still, you don't care. But if you scale this 6 orders of magnitude, you now get 1 input per minute. So you want to choose that 1 input very, 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 very carefully, because you will be able to execute the next one only next minute. And the second thing is that the fuzzer needs to be best effort, because you can get definitive answers for almost anything. You can understand, does it give new coverage, or even did it crash, or is this program reproduce the same crash we seen here? And the fuzzer needs to kind of operate in this context still. Okay, so this is the problem space. Now, how we solve those problems? First of all, let's start with the input. So what we would want to have as an input for a kernel fuzzer is something like this, like a C program that executes some system calls, right? And initially, we even considered the possibility of taking user space fuzzer and then trying to compile its output as a C program and then execute that C program. But we decided that probably won't be too efficient, because most of the time it will just won't compile. So we decided to go with the approach called structured fuzzing. And structured fuzzing is when the fuzzer actually knows about the structure of the input and can do much more sensible mutation of the input. And we started with the system call description language, which we now call syslang. You can see example of the description on the slide, and hopefully you can read it, mostly because those descriptions are similar to C function declarations. So we say that there is an open system call, which has first argument file, which is a pointer to file name, and the second argument is some flags, and it returns a file descriptor. And we can enumerate the values for the flags we can pass. And then we say there is a close system call that accepts the file descriptor. So we will look at more features of this language, but question you may have now is why don't we just reuse the existing C headers, because they already contain definitions of those functions. So there is a set of issues. For example, file descriptor is usually described just as an integer, right? But it's not exactly the integer. It's quite special type of integer for us, and most likely want to know that it's a file descriptor. Or const star. You may guess that it's a string, but what type of string is it? Is it a file system name? Is it a crypt algorithm name? Or is it a file name? Which is also quite special in the context of a system call fuzzer. Right, and there are lots of things like this integer must specify size of that array or size of that object. Or some things that you just simply cannot describe in C. For example, if you have a variable size array inside of a structure, C can only describe static layout. It can describe something like a network packet format. Now, other cases, for example, ioctl of write, which just accept a void star, but there's actually very interesting and complex things behind that void star. And there are more issues. So if that would be just one of those things, we maybe try to somehow work around that. But because it's this whole set of issues, we decided that it's just C headers don't contain enough information for us. Okay, let's look at other features. One of the main features is called resources, and resources is something that we need to pass from output of one system call to input of another system call. And the best example of this is a file descriptor. So the language allows you to describe this. You say that there is a resource called fd, and the base type for it is an int32. So if it's inside of a structure, it will take 4 bytes. And optionally, you can specify a set of special values for this resource. Those values are something that fuzzer can use directly. It doesn't need to call other system calls to kind of obtain those values. And then we say that open system call returns this thing called fd, and the closed system call accepts this thing called fd. And we can describe more complex things. In particular, we have resource inheritance. You can say that there is a fd CD-ROM, which is fd, but it's more specialized type of fd. And if you open this particular file, def/CD-ROM, then this gives you not just fd, but this more specialized type. And then you can attach, for example, set of ioctals to this more specialized type. Okay, we also can describe structures. So for structure, you give it a name, and on the left we have field names, on the right we have types, so it's a swap from C, deal with it. And for fields, we have such simple things as, say, integer, but we also can describe some things that you cannot describe in C. For example, you can place in a variable size array in the middle of a structure. So in this case, it doesn't mean an indirection, so it's not a pointer to an array. It's literally an array within the structure itself. And in this case, frequently you also have another field, integer field, that will contain the size of this array so that kernel can actually parse this structure. And we also can describe that as well. So when we generate a particular instance of this structure, as I said, this will be just a single chunk of memory where we will have, say, three integers first and then some number of elements for the arrays. Okay, we also have support for unions. And for unions, important thing is that they're denoted by the square bracket, where structs are denoted by the curly brace. So that's how you distinguish them. You can use you can have several options, and you can use any types for them. So at runtime, one of them will be chosen. An interesting thing is this varlen attribute, which stands for variable length. It's again an extension for C. So if you don't specify this attribute, then this union will work as a normal C union, which means that the total size of the union will be equal to the maximum size of all options. And if you actually use smaller option, that there will be some padding at the end to the maximum size. But if you specify this varlen attribute, then the dynamic size of the union will be equal exactly to the option that we choose, and there will be no padding at the end. This is also used quite extensively for kernel interfaces. Okay, so let's look at an example how we can describe, for example, this thing. Let's say we want to describe mount system call, and it accepts, in particular, a string which contains a set of arguments, each of which has a name, equals, and a value. Values can be different. Some arguments don't have values. So let's start bottom up. First of all, we describe UID option as a structure. First field contains a string, UID equals. Then a second field contains UID resource formatted as a decimal number. Similarly, we describe PID option. We just use the PID resource. And similarly, block options. But here we use flex type, which allows you to specify concrete values that are interesting for this particular variable. And then we have the option as a union with all of our existing options. And we use this varlen attribute because we don't want any padding at the end. And finally, we describe option with comma, which is again a structure. It contains our option union and a comma byte after it. And finally, we can describe the mount system call as accepting pointer to an array of such option with comma. So you may not think of a string as an array of structures, but why not? We actually can describe it this way. And these descriptions will allow fuzzer to generate strings that look like this, with random number of arguments, with random order of arguments, with random values, and so on. Okay, and some other features I will mention briefly. So we have plain integers, we have constants, we have flags, which work like C and nums. We have ranged integers, we have support for bit fields, also big endian integers, and you can say, for example, something like int32, which is big endian, so you need to swap bytes, but it's in the middle of a bit fields and only take 11 bits. And for the values, we want values in the range from 100 to 200 with a step 3, so 100, 103, 106. So it's a bit of an extreme example, but all those features are composable, and you can write this. Also, we have fixed size arrays, range size arrays. We have structures that are packed, aligned, padded. We can say that this integer is the length of that array or size of that object in bytes, or size of that object in 4-byte units or in bits. And we even have templates. And with templates, we also get the void type. And so some other features. OK, so this is for descriptions. The next thing is programs. And programs is what actually represent an input in our fuzzer. So that's what we mutate, that's what we add to the corpus. And program is what you may expect it is. It is a sequence of system calls with concrete values for all arguments. So for pointers, we have chosen exact addresses. For integers, we choose an exact values, and so on. And here you can see how resources work and why we bother to describe them. So we have notion of local variables, and open returns an FD. We assign it to a local variable R0, and then later we use it. OK, so if descriptions is something that you write and you give it to the fuzzer, then programs, they are manipulated by the fuzzer itself. Normally, you don't write them, and you don't even see them. Because based on the description, fuzzer can generate the programs from scratch. It can also mutate existing programs. It can also minimize programs. For example, does this minimized program still gives the same new coverage, or does it still crash the kernel? Or we can do some analysis on the program. We can also interpret the program or actually execute the system calls. And we can also convert them to more or less equivalent C programs, and we can serialize and deserialize them to such text representation. So let's look at some of the mutations. Because we have lots of information about the structure, we can do very smart mutations. So for example, we can insert or remove new system calls. Or we can change a particular argument. And we do this having the knowledge about the type of this concrete argument. So we can change size of an arrays, we can change options in unions, we can generate a file name knowing that this is file name, and so on. If there are any blobs involved, we also use traditional mutations of blobs, like flipping bytes or inserting, or flipping bits or inserting or removing bytes. And we can also do splicing of programs on system call level. So splicing is when you take two programs or some subset of system calls and you merge them in some way. And we do this based on resources. So resources help to, first of all, choose the program. Say this program works with a TCP socket, so we probably want to take another program that makes some use of TCP socket to splice. And also helps to select system calls that we want to merge. For example, if we take a setsoc system call, we probably also want to take the socket system call that creates that socket as well. OK, so descriptions help being smarter. But another part is prioritization. The thing is that the whole search space is enormous. But actually, the interesting part of that search space is very tiny. The part that actually will give any meaningful coverage, because the majority will just bail out immediately. And if we just sample this whole large space uniformly, then most likely we're testing not interesting programs all the time. So actually, you want to aim this small part that is interesting. So for this, we use prioritization throughout the fuzzer. For example, when we choose a program from a corpus, we look at its complexity and coverage. For example, we may have one program with just one system call, for example, shed yield, which doesn't accept any arguments. And we have another program with 10 system calls with complex arguments. Right? We want to mutate both of them, but we want to drive more mutations to that more complex and larger program. Also, when we choose mutation action, for example, do we want to insert a call or remove a call or change an argument, there are some priorities. For example, it turns out that it's much more profitable to insert system call rather than remove. Removing a system call can give some new behaviors, but usually it doesn't. Also, when we insert in a new system call, we have set of priorities for this. First of all, we look at argument complexity again. We may have a shed yield system call which doesn't have any arguments, and another system call with very complex arguments and large search space. So we want to test both, but again, we want to drive testing towards that more complex system call. We also look at the static relations between system calls. If we have a program that works with the sockets, we probably want to add another system call that works with the sockets rather than, say, with the file system. And we learn some dynamic relations, which is similar to reinforcement learning. For example, we notice that in corpus, those two system calls frequently appear together. We don't know why they appear together, but we just see that like there's must be some relation between them. So if we see that, we start also inserting those two system calls into programs more frequently. When we select argument for mutations, we have some objective criteria, which is based on the domain space of this argument. For example, we have int 8 and int 64. And we want to mutate int 64 more just because it has much more values to try. And we also have some subjective criteria, which is based on heuristics. For example, we notice that changing exact values of pointers usually doesn't provoke any new behaviors and usually doesn't trigger bugs. So initially, we assumed that it's important, but later it turned out that it's not too important, so we started doing this mutation less frequently. And when we generate or change a particular argument type, we also have lots of heuristics. For example, if it's a resource, how frequently you pass -1 for FD, or if you have an int, how frequently you use 0 value, which is kind of special, so you want to use it more than all other values, but you need to choose some probability for this. So this prioritization is used throughout the fuzzer on multiple levels. Okay, blocking system calls. I mentioned if you say create a pipe and you try to read from this pipe, this will block because the pipe is empty. But later you may have a call that actually writes to the pipe, and this write would unblock the read if we execute it. So here we want two things. One, we want to get past the read in some way. And second, we actually want to execute this unblocking path in the read and collect the coverage from it, because most likely this path from unblocking is different from the path when you go through read without blocking. So what we do is pretty simple. We call it threaded execution mode. We dispatch each system call to a separate worker thread. And if we see that, and we have some timeout, if we see that the system call doesn't return after that timeout, we consider that it blocked, and we just dispatch the next system call to another worker thread. But we still look for the previous system call, and if that read later returns, then we still collect the coverage from it and handle and understand that it was unblocked. So no rocket science here, but more interesting thing is called collide mode, and it helps us to provoke data races. So it works in the following way. We simply consider that every second system call is blocked right away. Let's look at the following program. So we start executing first open, we dispatch it to a thread, and then we immediately consider that it's blocked and immediately start the second one. So we start the two opens at roughly the same time. Then we wait for the second of the system calls, and then we again dispatch next two system calls almost together. And this potentially may help provoke the race between those system calls. So it's a pretty simple strategy, but it helped us to find lots and lots of races already. Then the next feature related to execution is fault injection. Fault injection is when you specifically fail some things for the purposes of testing error handling paths. You can fail malloc, you can fail I/O operations, some other things, and it's actually meaningful for kernel. So most of user space programs, even if they try to handle out of memory, usually that's not tested, and usually they simply crash. But the kernel actually needs to survive. It needs to survive low memory conditions, and needs to survive hardware failures, and so on. And it turns out that since kernel is written in C, with manual resource management, approximately 1/3 of kernel code is actually error handling paths. And they're specifically tested very, very well, almost untested. And lots of them contain bugs like use of the free and double freeze, because that's a path when you actually, free things and so on. So there was existing fault injection. Oops. Sorry, it stopped working. It's just, okay. Thank you. Sorry. So there was old fault injection facility in the kernel, and it worked in the following way. You can just ask kernel to fail X% of potential failure sites. For example, say fail 1% of things. But this approach will both fail things that we don't want to fail, and it will not necessarily fail the things we want to fail, and it just doesn't allow us to understand how well we actually tested the kernel. So we did a slightly different thing. We did what we call systematic fault injection. It has two primitives. One, you can ask kernel to fail the next nth failure site in the current thread. And the second thing, you can ask kernel if the failure was injected. And this can be used in the following way. Let's say we see new coverage on some system call. So what we do, we then execute this program again, and we ask kernel to fail first failure site in this system call. Then if the failure was injected, then we execute this program again, but now we ask to fail the second failure site in this system call. Again, if it was injected, we try to fail the third site, and so on, until actually the kernel says the failure wasn't injected, which means that we tested all error paths in this system call one by one. And since we do this whenever we get new coverage, the expectation is that we actually tested all error paths in the whole code that we ever covered. So this mode works much better, and it actually, like with a minimum number of iterations, it allows you to have some understanding that you actually tested all possible cases. Okay, coverage. So for coverage, we use compiler instrumentation. It's supported both by GC and LLVM. And the compiler inserts a function call into every basic block of code. Basic block is roughly a piece of code without branches. And the rest happens in the runtime. So we have a buffer that is shared between kernel and user space, and this buffer contains a trace of traces kernel code execution. So the first word of this buffer contains number of subsequent elements in the trace buffer, and the remaining elements are the program counters from the kernel. So the kernel coverage callback does two things. First of all, it increments the first word, and it adds the current PC to the end of the trace buffer. And the user space can do two things. First of all, it can write 0 to the first element, which will effectively reset the coverage, because then the kernel will continue, again, filling this buffer from the beginning. And it can read the currently filled part and use it. So a few things to note. First of all, this is per thread. So the tracing happens per thread, but you can set up those buffers for multiple threads independently. Interrupts are completely ignored. We don't trace them, we only trace the currently executing system call. And some parts of the kernel are not instrumented for coverage. For example, memory allocator and scheduler. So this helps. So this organization is quite efficient, because you don't need to do any system calls to start tracing, start collecting coverage, finish collecting coverage. User space can just directly read the buffer. And also it helps with some of the flakes. Because we ignore interrupts, we ignore schedulers. So flakes is some coverage that you see on when you execute a system call, but then you execute it next time and you don't see this coverage. And this is a problem for kernel. And Kcov doesn't completely solve it. So we have another logical layer on top to remove more flakes. In user space, you usually have a concept of corpus coverage. So it's a union of coverage of all inputs in the corpus, and that's what you use to understand if current input gives you new coverage on top of it. So first of all, we don't have one coverage. We have now max coverage and min coverage. So if we get some coverage within the max coverage, then this is not new. We just immediately discard those inputs. But if we have something that gives us new coverage on top of max coverage, then at this point, this may be something interesting. Maybe we get new coverage. But it still doesn't mean that it's necessary new coverage, because it may be just flakes. We want to ensure that we actually can get reliable coverage. So what we do, we then execute the system call again several times, and we see what coverage we get. So, and we remove the parts that were flakes that we didn't get on the next subsequent iterations. Potentially, we'll remove all of the new coverage, and then we'll see, okay, all new coverage is actually flakes, so it's not the new coverage. In that case, we'll throw the input away. Otherwise, if even after several iterations, we still see that we're getting new coverage, at that point only we add it to the corpus. But in all cases, we add it to the max coverage because we've seen this coverage and we don't want to handle this flake again in future. Okay, so this is it for implementation. Now the question you may have, does it work, and like, is all of this complexity worth it? And I can say, oh yes. So this is just one randomly picked example. On the left, you can see the random program that the fuzzer generated. It tried to open some device and then call some ioctal. On the left, you can see ascend, out of bounds report, similar to what you usually see in user space with the call trace, allocation stack, and Fritz stack. So when I implemented the fuzzer, all the basic parts, we started getting bugs. And then as we made it more smart and we added more descriptions, we started getting even more bugs. And at some point, we started getting so many bugs that my full-time job became just sending bug reports. So literally, I sit every day and just entered emails composed like this is the crash, this is the reproducer, it happened on that commit, find the people to send it, and I did it literally for months. So initially it was fun, but soon it stopped being fun. I reported about 500 bugs, at which point I decided that we probably need to somehow solve it. Okay, and we built a system called sysbot, which provides even higher level automation on top of the fuzzer. So it does several things. It does continuous kernel build. It also does continuous syzkaller build, so it updates both. And then it starts fuzzing. And fuzzing includes also deduplication, report symbolization, and other things. At some point, it finds a bug, and maybe even a reproducer for this bug. If we get a reproducer, we can do bisection, and then we can report the bug. We find the people to send this bug report. We compose the actual email text, and we send it to kernel mailing lists. Then a kernel developer may ask sysbot to test a potential fix for this bug. And it can also say that this bug is fixed by a particular commit. And developers do this by including a special tag into commit message, which says that this commit fixes that sysbot bug. At this point, sysbot will understand that there is a fix for that bug, and it will wait when this fix actually reaches all of the builds that we have. And when we have it in all builds, we know that this crash will not happen anymore, and at this point, we close the bug. Also, a few potential alternative paths. One is that developer may say that this bug is a duplicate of that other bug, or this bug is invalid, or if we can do fix bisection. For example, if we notice that it stopped happening for some time, we can do fix bisection and say, hey, we think that this bug was fixed by this commit. Or if it doesn't have a reproducer, we have some logic to auto close the bugs after some time. Okay, here you can see an example of an email that the sysbot has composed. It includes some information about the commit, links to reproducers, to other crashes, the, say, ASAN report message, and some footer. So this message took a lot of time to kind of refine, and when we just let the bot loose and start sending emails to mailing lists, this is a very fun time. So for example, this table at the top, it was a topic of very lengthy discussion of how exactly it needs to be table formatted and like how you need to lay it out. Or at the bottom we say this bug was generated by a bot. Previously we said this bug is generated by a dumb bot because I thought it's kind of fun irony. But some people were angry on the bot and they used it as an offense and they said, hey, you yourself said that your bot is dumb, so why do you let it send emails to us? So then we removed that wording. And also the sysbot engineers can be reached at was also very specifically requested like sentence that we need to include in the text. Okay, so quick rewind to today. For upstream Linux kernel, we found about 2,900 bugs that were automatically reported by the system. About 2,000 are fixed. 800 are still not fixed. So the system runs for about 2.5 years, which makes it 3 bugs per day reported each day, and 2 of which are fixed. And before that, we also reported about 1,000 of bugs manually. So we have a web dashboard which has all of the bugs and all of the statuses which are open, which are fixed. Here you can see a snippet of open bugs for Linux kernel. Some section with use after freeze and out of bounds. We say when it was reported. Some were reported, say, 2 years ago, but they still happen, has a reproducer. This is the number of bugs we report per month. Now we report from about 100 to 200 bugs per month. You can see it's pretty random. Sometimes we add some new features. Sometimes there's a new code being merged in the kernel. So people ask if it's getting better. So I can say that it's getting better. It's still pretty random. But sysbot allowed us to scale the system even more. So besides upstream Linux, we also test several kernel releases. We test several Android releases. We test a number of internal kernels, and we also ported syzkaller to a set of other operating systems like gvisor, Fuchsia, FreeBSD, NetBSD, OpenBSD. So in total, it reported actually close to 7,000 bugs by now. And this doesn't include all of the invalid and duplicate bugs. So you may wonder what types of bugs we're finding. So we're finding all types of bugs, not necessarily use after free, out of bounds. We enable lots of debugging tools, and we find just some mix of them. I think we found at least several thousands of security bugs, but very few of them actually were assessed and have CVEs. But for kernel, we noticed some interesting bugs. For example, a thing like warning, which is kind of an assert in the kernel world, can be a very interesting bug. We've seen a case where we get a warning, but this is actually a warning to restore register on the context switch to a guest virtual machine, which means that we leak all of the host registers to the guest, which is pretty substantial information leak. And we've seen some remote exploits, and we see also a case when the machine was unresponsive, but it turned out to be full guest-to-host escape because there was a page reference leak triggered by a guest. So by executing one instruction, a guest could trigger a page reference leak on the host. Okay, I'm running out of time, so future work. We have lots of work. We need more descriptions. We need We are working on auto-generating some descriptions. We want smarter fuzzing because we have lots and lots of information about all of the structure and resources and system call return values. We also want to make triggering races smarter. And we want to extend it to maybe things like hypervisors, maybe even some user space libraries, because this fuzzing engine is pretty generic. So there are parts that are kernel specific, but parts are also very generic. Again, Windows, so you've seen Windows mentioned yesterday on the keynote. You see Windows mentioned yesterday in another talk, and you see there's another port to Windows done by other people, and there's yet another port done by yet another people. All of those ports are closed. We asked some people if they want to open source their work and contribute back, and they said, no, we will not make it public at least in a year because it still finds too many good bugs. And some of the bugs are for VSL. Well, let's say that not to elaborate. Okay, so I hope to see Windows port in some future. And thank you. All of this is open source.